All right, let's just run quickly. These problems can go by very fast when you're looking at symmetry. So notice I can see that this is a linear equation, 7y equals 6x plus 7, and I could actually solve it for y. And why I would do that is I would see that my slope 6, 7 is positive, so I know it's either A or D. And then when I divided everything by 7, the y-intercept would be 1. So if I enlarge this to find this, I can see that that is my actual function. Anytime you have a line, it is symmetric with the origin only if it goes through the origin. Well, this doesn't go through the origin, so this is no symmetry at all. All right, so now the next one, I can see that this is a parabola. The value on the x squared is positive even when you divide by 2. So I know this is going to be concave up, so I have the choice of these two. Once again, if I'm dividing everything by 2, I can see that this is going to be -3/2, so it's going to be below, it's going to be moved below. And then if I cut this in half on the y-axis, I can see that it is symmetric to the y-axis. And then just kind of running through these, I can see here if I solve this for y, okay, so solving this for y, I would get -3y equals -3x. I divide both sides by -3. And I get basically y equals x, so it does actually go through the origin. Remember, a line, whenever you have a line, is going to be symmetric with the origin if it goes through the origin. All right, I'm looking here. I see even values, so whenever I have my even values, it looks like this is going to be symmetric with the y-axis. But notice, think about if you're plugging in, going back to symmetry, if your exponent I'm looking at is even, okay, and your y exponent is even, so remember the y would be for the x-axis, and then if they're both even numbers, then it's also going to go through the origin as well. And that was an example that I did earlier on this one. If I'm looking at an actual point, and if I want to see it's symmetric with respect to the x-axis, remember when it's symmetric to the x-axis, that means it's the negative y. When it's symmetric with the y-axis, it's the negative x, so negative and a negative, but then the same y. When it's symmetric with the origin, you negative the x and you negative the y. Looking here, I can see if I cut this right down, so it's asking if it's even, odd, or neither. And in fact, going back and looking here, notice even functions are symmetric with the y-axis. Cut this down, definitely would be even. Looking at this function here, it's definitely not even because it's not symmetric with the y. It would be odd, being symmetric through the origin. You could solve these with points, but I can kind of see going through the origin this way and this way, these would be the same. This one is very tricky, and I'll tell you the reason why that it's very tricky is this open circle, and you might need to see it. So notice that the negative x did become the positive x, but the negative y didn't become the positive y because of that open circle. Whether a function even, odd, or neither, look at your exponents. Every exponent is odd, so I know this is an odd function, and it's going to be the negative 3x to the 7th minus 2x, because if you plugged in negative x to an odd, that's going to become negative. And once again, all my exponents are odd, so this would be odd. I can see both of these are odd. My exponents are odd, 7 and 5, so this would be odd. I can see this is going to be an even because my exponents are even. Remember, when you plug in negative x to an even, it just goes back and becomes positive, 4x to the fourth minus 6, and this would be an even function. And then finally here, I can see this is kind of crazy, right? But if I put a line on the, or a mirror on the x-axis, it looks like it's symmetric with the x-axis. Would it also be symmetric with the origin? No, because we can see that in this case, my x doesn't become a negative x, and my y does not become a negative y for both. And that's just a quick overview of that homework.